Welcome back to Night Cosmos Sleep, where we journey together through the distant reaches of the universe, listen to stories written in the light of the stars, and slowly explore worlds that exist far beyond the familiar boundaries of Earth. Thank you for spending this time with us on today's journey. Find a position that feels completely comfortable. Allow your breathing to gradually slow. Let the sounds around you drift a little farther away, and gently turn your attention toward a faint point of light in the northern sky, where a planet more Earth-like than scientists once believed is quietly orbiting its star. That world lies nearly 25 light-years away. In everyday life, such a distance is almost impossible to imagine. Light, which can circle Earth more than 7 times in a single second, still needs roughly a quarter of a century to cross the space between these two star systems. The rays now reaching telescopes on Earth left that distant star many years ago, at a time when each of our lives may have looked very different. While that light traveled silently through space, the planet known as GJ 3378b completed hundreds of orbits around its star, passing through hundreds of what we might call years, even though a year there lasts only a little more than 3 Earth weeks. Placed against the scale of the Milky Way, however, a distance of 25 light-years seems surprisingly close. Our galaxy stretches across roughly 100,000 light-years and contains hundreds of billions of stars, along with countless planets that have yet to be discovered. Within that immense expanse, GJ 3378 is almost part of the Sun's local neighborhood, like a house not too far away in a vast city whose roads remain mostly unexplored. Yet despite being nearby by astronomical standards, the planet orbiting that star has never been seen directly by human eyes. No image can tell us what color its surface might be, whether clouds move through its sky, or whether it holds mountains, ice, oceans, or only broad plains of stone beneath the dim red light of a small star. What we know about GJ 3378b does not come from an image of the planet itself, but from a very slight motion in the star it orbits. That star is a red dwarf, far smaller, cooler, and fainter than the Sunday. To the naked eye, it nearly disappears among the countless points of light in the sky. But as the planet moves along its orbit, its gravity pulls the star slightly away from its resting position. This subtle wobble changes the star's velocity by an amount comparable to the speed of a person walking slowly. Even from 25 light-years away, instruments on Earth can detect that delicate rhythm, much like hearing a faint sound coming from the far side of a very large room. When GJ 3378b was first studied, the measurements suggested that it might be more than 5 times as massive as Earth. At that mass, the planet seemed likely to belong to the group of worlds known as mini-Neptunes, perhaps surrounded by a thick envelope of gas around its interior, and very different from Earth's familiar rocky surface. Such a planet would still be fascinating, but it would be far less like the kind of place we imagine when we think of oceans, continents, or an atmosphere thin enough for starlight to reach the ground. Then new observations were gathered. For years, telescopes continued to monitor the star's light, recording hundreds of measurements and comparing data from several different instruments. As the signals became clearer, scientists realized that the earlier numbers needed to be revised. A year on GJ 3378b does not last nearly 25 days, as once estimated, but about 21.45 days. More importantly, the planet's minimum mass is not more than 5 times that of Earth, but only about 2.3 times greater. That change may appear to be nothing more than a few numbers in a table, yet it transforms almost everything about how we picture this planet. A world with roughly 2.3 times Earth's mass is more likely to be rocky than a small ball of gas. It may have a solid surface beneath an atmosphere, although we still do not know whether such an atmosphere truly exists. The planet also receives about 90% of the energy Earth receives from the Sun, placing it in a region where temperatures could theoretically allow liquid water to exist, provided that the planet has suitable pressure, an atmosphere, and the right surface conditions. This is why GJ 378b quickly became one of the most intriguing nearby worlds in the search for life beyond the solar system. But this is also where we need to slow down before using appealing labels such as a second Earth. A planet's location within the habitable zone does not mean that it has oceans, forests, or any form of life. Mars once had water flowing across its surface, yet today it is mostly a cold, dry desert. Venus is nearly the same size as Earth, but its dense atmosphere has turned its surface into a world hot enough to melt lead. Distance from a star is only one part of the story. Whether a planet can truly remain gentle enough for water and life also depends on its formation history, the composition of its atmosphere, the activity of its star, and its ability to hold on to that atmosphere over billions of years. The star GJ 3378, though small and faint, may also pose the greatest threat to its planet. Red dwarfs often pass through periods of intense activity, releasing X-rays, ultraviolet radiation, and streams of high-energy particles. A planet close enough to its star to receive sufficient warmth must also endure a harsher radiation environment. Over immense spans of time, those waves of energy can erode an atmosphere, stripping gas away piece by piece and carrying it into space. GJ 3378b may therefore be a world that still retains an atmosphere thick enough to protect its surface, or it may be a rocky sphere that lost most of its air long ago. For now, both possibilities remain open. We know the planet exists. We know the rhythm of its orbit, the gravitational pull that makes its star wobble, and the amount of energy it receives, which is close to what Earth receives from the Sunday. But we do not know its true size or density. We do not know whether it has an atmosphere, water, or exposed rock beneath the light of its star. The most important truths about this world remain beyond our sight, like a room whose presence can only be sensed through footsteps echoing from behind a closed door. Perhaps it is this incompleteness that makes GJ 3378b so compelling. It is not a world proven to resemble Earth, but one that is close enough and promising enough for the question to be asked seriously. Each new measurement does more than add another number. It brings us closer to understanding whether small planets around red dwarfs can preserve their atmospheres, sustain liquid water, and perhaps become places where life could begin. 25 light-years away, GJ 3378b continues to circle its small star, entirely unaware that light from its system is being collected by telescopes on a distant planet. And here on Earth, our journey will begin with that faint star itself, as we explore why these small red dwarfs have become some of the most important places in the search for potentially habitable worlds throughout the Milky Way. In the northern sky, among the unremarkable stars of the constellation Camelopardalis, there is a point of light so faint that it is nearly impossible to see with the naked eye. It does not shine like Sirius, it does not display the distinct color of the large stars visible at night, and it is not among the celestial objects that once guided sailors or appeared in ancient stories. This star is small, cool, and discreet, quietly existing in the sun's neighborhood, even though most people have never heard its name. Astronomers call it GJ 3378. Light from GJ 3378 takes about 25 years to reach Earth. In a human lifetime, 25 years is long enough for a child to grow up, for a city's skyline to change, or for technologies once considered new to become familiar. But on the scale of the galaxy, that distance is close enough for GJ 3378 to be considered one of the solar system's neighbors. The Milky Way spans roughly 100,000 light-years. If the entire galaxy were reduced to the size of a vast city, the solar system and GJ 3378 would not lie at opposite ends, but would be more like houses within the same neighborhood. Light from the far side of the galaxy may need tens of thousands of years to reach us, while light from GJ 3378 takes only a quarter of a century. That closeness does not make it easy for humans to travel there, but it does make the star a valuable target for telescopes searching for small planets beyond the solar system. GJ 3378 belongs to the group known as red dwarfs, the most common type of star in the Milky Way. In this name, the word dwarf does not mean that the star is old, fading, or close to disappearing. It simply refers to its much smaller size compared with the Sunday. GJ 3378 has only about 1/4 of the Sun's mass, and its radius is less than 1/3 that of the star that illuminates Earth. If GJ 3378 could be placed beside the Sun, the difference would be unmistakable. The Sun is a sphere of plasma nearly 1.4 million kilometers across, large enough for more than 1 million Earths to fit inside it by volume. GJ 3378 is much smaller, yet it is still a true star, where matter at the core is compressed to densities and temperatures high enough for hydrogen to fuse into helium, releasing energy through a process that can continue for spans of time that are difficult to imagine. The surface of the Sun has a temperature of nearly 5,800 Kelvin. GJ 3378 is only about 3,300 Kelvin. It is still far hotter than any flame on Earth, but in the realm of stars, that temperature is relatively low. This cooler surface shifts much of the star's light toward red and infrared wavelengths, making it appear faint to human eyes. A red dwarf would not necessarily look like a vivid red sphere to someone standing near it. The color perceived by the human eye would also depend on the intensity of the light, the atmosphere, and the way different wavelengths were scattered. But according to its emission spectrum, GJ 3378 produces more light in the red and infrared regions than the Sunday. To ordinary telescopes that are most sensitive to visible light, it can easily disappear into the background of the sky. Only when instruments designed to observe infrared wavelengths are used does this small star begin to reveal more information. The faintness of GJ 3378 is not unusual. Most stars in the galaxy may be red dwarfs. Estimates commonly suggest that they make up around 70% of all stars in the Milky Way. This means that when we look at the galaxy as a whole, the bright stars easily visible to the human eye represent only a small part of its true population. Most of the Milky Way's inhabitants are small, cool, persistent stars, hidden in the darkness between more prominent points of light. Their abundance places red dwarfs at the center of an important question. If most stars are red dwarfs, then most planets in the galaxy may also orbit stars of this kind. When searching for places capable of sustaining liquid water or life, looking only at stars similar to the Sun would mean overlooking most of the planetary systems that exist. For a long time, red dwarfs were not considered ideal places for life. They are small, faint, and often magnetically active. Many stars in this group produce flares that can suddenly increase the amount of ultraviolet and X-ray radiation in the surrounding space. Planets must orbit relatively close to receive enough warmth because red dwarfs emit far less light and energy than the Sunday. That proximity leaves them more exposed to radiation and stellar winds. Yet the need to orbit close to the star also offers an advantage for observation. When a planet lies near its host star, its orbit is usually shorter, its gravitational pull on the star is easier to detect, and many complete orbits can be recorded within a relatively brief period. A planet that takes 1 Earth year to complete its orbit produces only 1 signal cycle each year. A planet with an orbital period of a little more than 20 days can repeat that signal more than 10 times within the same span. GJ 3378b completes 1 orbit around its star in only about 21.45 days. A year there is shorter than a month on Earth. While Earth travels nearly 940 million kilometers to complete a single orbit around the Sun, GJ 3378b follows a much smaller path around its own star. The planet's average distance from GJ 3378 is only about 0.097 astronomical units, or roughly 14.5 million kilometers. If that orbit were placed within the solar system, the planet would lie even closer to the Sun than Mercury. Mercury orbits at an average distance of about 58 million kilometers, nearly 4 times the separation between GJ 378b and its host star. A world orbiting so close might seem as though it should be unbearably hot, but that comparison would only be valid if both stars released similar amounts of energy. GJ 378 is far less luminous than the Sunday. A planet must move much closer to it to receive enough light to avoid becoming a completely frozen world. Although GJ 378b travels along a very tight orbit, it receives only about 90% of the energy Earth receives from the Sunday. In terms of average incoming radiation alone, it does not exist in an environment as hot as Mercury's. Instead, it occupies a region where theoretical temperatures may approach the range that allows liquid water to exist, provided the planet has a suitable atmosphere. This is why the habitable zone around a red dwarf lies so close to the star. The zone is not the same size in every planetary system. Around stars hotter and brighter than the Sun, it may lie much farther away. Around small, faint red dwarfs, it contracts into a narrow band close to the star. The position of GJ 378b places it within a region considered promising. But distance is only the first part of the story. A planet is like a stone placed beside a fire, whose temperature depends on more than its distance from the flames. The color of its surface, its ability to absorb heat, the layer of gas surrounding it, and the way that heat is distributed can all lead to very different outcomes. Two planets receiving nearly the same amount of energy may still develop completely opposite climates. A world with a thick atmosphere may retain heat efficiently, while a world without air may warm rapidly in the light and cool just as quickly when it falls into darkness. GJ 378b also raises another possibility commonly associated with planets orbiting close to red dwarfs: tidal locking. The star's gravity may have gradually slowed the planet's rotation until the time required to turn once on its axis became equal to the time required to complete one orbit. If this has happened, one side of GJ 378b may always face the star, while the other remains in prolonged darkness. Tidal locking does not necessarily mean that a planet cannot support life. The moon is tidally locked to Earth, which is why we always see nearly the same side of it. On a planet with a sufficiently thick atmosphere or an ocean, winds and currents could transport heat from the illuminated hemisphere to the dark side. Instead of experiencing alternating days and nights, the world might have a region of permanent daylight, a region of permanent darkness, and a broad band of endless twilight between them. Along the boundary between day and night, the star might always remain low near the horizon. Dim red light could stretch across a region of the surface that never fully reaches noon and never falls completely into night. It is a compelling image, but for now, it remains only a possibility. We do not know the rotational speed of GJ 378b, and no available data allows us to describe its climate or sky with any precision. What can be said with greater confidence is that its host star will survive for an extraordinarily long time. Small stars consume their fuel more slowly than larger ones. The Sun is expected to remain in its stable phase for about 10 billion years, while low-mass red dwarfs may continue shining for hundreds of billions or even trillions of years, depending on their mass. The universe itself is only about 13.8 billion years old, which means that no small red dwarf has yet had enough time to complete its entire natural life cycle. This endurance creates an immense span of time for chemical processes to develop on the planets orbiting these stars. On Earth, life appeared relatively early in the planet's history, but billions of years were required for simple organisms to give rise to complex ecosystems. A star capable of providing stable light for an extremely long time would seem to offer more opportunities. Yet a long lifespan does not mean that the entire history of a red dwarf is peaceful. When young, these stars can be far more active than they are today. The early stage of a red dwarf often lasts for a long time, while the star contracts and releases more energy than it will during its later, stable state. A planet that now lies within the habitable zone may once have endured a much hotter period, when water evaporated into the upper atmosphere, where it could be broken apart and gradually lost to space. GJ 3378 does not provide us with a complete record of its youth. Astronomers can measure its present light, observe its magnetic activity, and compare it with similar stars, but they cannot turn back time to directly witness what happened billions of years ago. For this reason, an important part of GJ 3378b's story lies within a history that telescopes can only infer indirectly. If the planet formed with abundant water and a thick atmosphere, its gravity may have helped it retain a significant portion of that material. With a minimum mass of about 2.3 times that of Earth, GJ 3378b may have stronger surface gravity than our planet, although the exact value depends on its radius, which has not yet been measured. A more massive planet may hold on to atmospheric molecules more effectively, but it may also have formed with a thick envelope of hydrogen and helium if it captured too much material from the disk of gas surrounding its young star. If it were possible to stand far enough away to see the entire GJ 3378 system, the view would probably look very different from the images commonly found in science books. The small star would sit near the center, emitting far less light than the Sunday. Around it, GJ 3378b would travel along a tight orbit, yet the planet itself would be almost completely lost in the glare of its host star. Even if a telescope could collect photons emitted or reflected by the planet's surface, that light would still be millions of times fainter than the star and would appear too close to it in the sky to be easily separated. From Earth, GJ 3378b does not appear as a point of light. There is no visible outline to reveal its shape, no color to tell us anything about its atmosphere, and no small shadow crossing the face of the star to signal that the planet is passing in front of it. This world was discovered in a more indirect way, by observing the motion of the star itself. A planet is not only held in orbit by the gravity of its star, it also pulls back on the star with its own gravitational force. The difference lies in their masses. GJ 3378 is far more massive than the planet, so its movement is much smaller, but it is never completely still. This can be imagined as an adult holding hands with a child while they turn together in a circle. The child moves along a wide path, while the adult only leans slightly and steps around a much smaller area. If the adult is far heavier, that motion becomes even more difficult to notice, but it is still there. In the same way, a star and its planet both orbit a shared balance point, commonly known as the system's center of mass. In the case of GJ 3378, this balance point lies very close to the star's interior. The planet completes broad loops around its host star, while the star makes only a slight motion in the opposite direction. From a distance of 25 light-years, astronomers cannot watch the star shift across the sky through each tiny orbit. Instead, they measure the portion of its motion directed toward or away from Earth. When GJ 3378 is pulled slightly toward us by the planet, its light changes in a very subtle way. When the star is pulled in the opposite direction, its light changes the other way. This phenomenon is based on the same principle as the changing sound of a vehicle passing someone standing beside the road. A car horn produces sound at a nearly constant frequency. As the car approaches, the sound waves are compressed in the direction of motion, causing the pitch to sound higher. After the car passes and moves away, the waves are stretched, making the pitch sound lower. The human ear can clearly detect this shift, even though the engine or horn itself has not actually changed. Light is also a wave, so it responds in a similar way. When a star moves toward Earth, its light waves are compressed slightly and shifted toward the blue end of the spectrum. When the star moves away, the wavelengths are stretched and shifted toward the red. Astronomers call this the Doppler effect. The movement of GJ 3378 is far too small to be noticed simply by looking at the star's color. It does not truly change from red to blue and then back again. The shift appears only in the positions of extremely narrow spectral lines, where elements in the star's atmosphere absorb part of its light. Each element leaves behind its own pattern of lines. Hydrogen absorbs light at certain wavelengths. Sodium leaves a different pattern, while iron, calcium, and many other elements create a complex system of fingerprints. When the entire star moves, all of these fingerprints shift together. By measuring their positions with extraordinary precision, researchers can determine how quickly the star is moving toward us or away from us. The influence of GJ 3378b causes the star's observed velocity to change by an amplitude of only about 1.3 meters per second. That is close to the speed of a person walking slowly. The star, located 25 light-years away, is moving through space at many much greater velocities, yet the instruments must isolate a wobble no faster than a human step. It is like standing on a windy shore, watching large waves continuously rise and fall while trying to detect a tiny ripple that returns at regular intervals every 21 days. That ripple is not only hidden by the larger waves, but also mixed with the effects of Earth's atmosphere, vibrations in the telescope, temperature changes inside the instruments, and natural activity on the surface of the star. A star is not a perfectly still sphere of light. Its surface contains magnetic regions, dark spots, bright areas, and moving plasma. As the star rotates, these structures gradually appear and disappear from our line of sight. They can alter the spectral lines in ways that closely resemble the signal produced by a planet. If a dark region lies on the part of the star's surface rotating toward Earth, it reduces some of the light that is shifting toward the blue. As that region moves to the opposite side, the effect changes direction. The result is that the star can produce an apparent velocity wobble even when no planet is pulling on it. Red dwarfs make this work even more difficult because they emit most of their energy in the infrared. Invisible light, GJ 3378, is extremely faint, making it hard for conventional instruments to collect enough photons for precise measurements. To listen for the motion of a star like this, astronomers need spectrographs designed specifically for infrared light. One of the most important instruments used for this purpose is the Habitable Zone Planet Finder, commonly known as HPF. It is installed on the Hobby Eberly telescope at McDonald Observatory in Texas. The telescope has an effective primary mirror diameter of about 10 meters, large enough to gather the faint light of red dwarfs located near the solar system. HPF does not photograph the planet. Instead, it separates the star's light into thousands of different wavelengths, producing a detailed spectrum. The system then tracks the positions of absorption lines and searches for extremely small shifts. To measure velocities on the order of 1 meter per second, the temperature and pressure inside the instrument must be controlled with great precision, because even a slight distortion in the optical components could create a signal larger than the effect of the planet. Researchers began collecting observations with HPF in late 2018. The monitoring continued for several years, through early 2025. Creating a data series long enough to reveal a repeating signal and test whether it remains stable over time. In total, the research team used 137 velocity measurements from HPF. 137 observations do not mean that the telescope simply looked at the star during 137 isolated moments. Each observation had to be scheduled according to the star's position in the sky, the weather, moonlight, atmospheric conditions, and the time allocated to many other research programs. Some nights may not have produced data of sufficient quality. Some measurements had to be discarded because of clouds, humidity, or instrument errors. Even after a clear spectrum had been recorded, the work was not finished. The star's light had to pass through Earth's atmosphere before reaching the telescope. Water vapor, oxygen, and many other molecules in our air absorb light at particular wavelengths, creating their own lines on top of the star's signal. These Earth-based lines had to be carefully identified and removed. The motion of Earth itself also had to be taken into account. Our planet rotates on its axis, travels around the Sun, and moves with the solar system through the Milky Way. Over the course of a day, the velocity of the observatory changes because of Earth's rotation. Over the course of a year, Earth's motion around the Sun produces changes far larger than the wobble caused by GJ 3378b. Computers must know the telescope's precise location, the exact time of each observation, and Earth's motion in order to subtract these effects. Only after the known movements have been removed can the small remaining variations be used to search for a planet. Alongside the HPF data, the researchers added 18 measurements from another instrument called NEAD, installed on the Wind Telescope at Kitt Peak National Observatory in Arizona. NEAD operates mainly in visible light and was also designed to measure stellar velocities with extremely high precision. 18 measurements are far fewer than the HPF observations, but they are valuable because they come from a completely different instrument. If both systems detect the same pattern of motion, the likelihood that the signal is merely an error unique to one instrument becomes smaller. Each device has its own optical design, operating environment, and method of processing data. A real planet should leave a consistent trace in every data set, even when their levels of noise are not the same. The researchers also combined observations from Carmenes and Spirou, two spectrographs that had previously been used to monitor GJ 3378. Carmenes operates at Calar Alto Observatory in Spain, while Spirou is installed on the Canada, France, Hawaii telescope at the summit of Mauna Kea. Both are capable of observing cool stars at red and infrared wavelengths. Combining data from 4 instruments is not as simple as placing all the numbers into a single table. Each instrument has its own velocity reference point, its own level of noise, and may respond differently to activity on the star. The research team had to construct a model for each data set, correct for systematic differences, and determine whether the 21.45 day signal appeared consistently across them all. A signal found in only one instrument could be a technical error. A signal present during only one observing season could come from temporary activity on the star. But a wobble that repeats over many years and is recorded by several spectrographs at different observatories is more likely to be the trace of a real object orbiting its host star. The long observing period also helps scientists distinguish an orbital period from other natural rhythms. If the star were monitored for only a few weeks, a slow variation could be mistaken for a planet. When the data extend across many years, the model must explain not merely 1 or 2 repetitions, but dozens of consecutive cycles. GJ 3378b completes one orbit in about 21.45 days. During 6 years of observations, the planet could have circled its host star more than 100 times. The telescopes did not follow every orbit, but measurements scattered across time still made it possible to reconstruct the repeating rhythm, much like hearing only a few notes from each passage of music, and still recognizing the melody as a whole. The difficulty is that observing schedules are never perfectly regular. A telescope can see the star only during certain seasons when it appears in the nighttime sky. Weather may create long gaps, while moonlight and the observatory's schedule can leave the measurements unevenly distributed. These gaps can sometimes produce false cycles in the analysis. A real signal appears several closely spaced periods when the data are sparse or interrupted. This is one reason the original results for GJ 378b were not entirely accurate. The first measurements suggested a period of about 24.73 days and a stronger velocity signal. Once more data became available, a new model showed that a rhythm closer to 21.45 days was a better fit. The change from 24 days to 21 may not seem large, but the orbital period is directly related to the planet's distance from its host star. A shorter period means the planet lies slightly closer to the star and completes its orbit more quickly. More importantly, identifying the correct period makes it possible to calculate the amplitude of the star's wobble more accurately, which in turn affects the estimated mass of the planet. When the data were still limited, some of the noise created by stellar activity may have been blended into the planetary signal, making the wobble appear stronger than it really was. If scientists believed the planet was pulling on the star with greater force, they would infer that the planet had a larger mass. Once new observations allowed the noise to be separated from the orbital signal, the velocity amplitude fell to about 1.3 meters per second, and the minimum mass of GJ 3378b decreased with it. To examine the star's activity, the researchers did not look only at velocity. They also monitored spectral lines sensitive to magnetic fields and active regions on the stellar surface. If a cycle appeared at the same time in indicators of stellar activity, it might not have been caused by a planet. If the velocity signal continued to repeat while the activity indicators did not vary with the same rhythm, the planetary explanation became stronger. The star's brightness was also examined. Star spots can cause GJ 378 to brighten and dim as it rotates. If the brightness period matched the velocity signal, researchers would need to consider whether surface activity was creating a false wobble. In the available data, however, the signal near 21 days is better explained by the orbital motion of a planet. Exoplanet discovery often unfolds in this way. There is no single moment when a telescope sees a tiny point and every question is immediately answered. Instead, there are years of accumulating faint measurements, testing different periods, removing noise, and comparing models. Each velocity measurement can be imagined as a single point on a graph. One point alone tells almost no story. When hundreds of points are placed at their proper positions in time, they begin to form a rising and falling curve. That curve shows the star moving toward us, slowing down, changing direction, and then retreating before the motion repeats. If the planet's orbit is nearly circular, the velocity curve has a smooth and regular shape. If the orbit is stretched into an ellipse, the changes in speed are less even because the planet moves faster when it approaches the star and more slowly when it travels farther away. The newer data suggests that the orbit of GJ 3378b may be close to circular, although the precision of the measurements still places limits on that conclusion. A nearly circular orbit would help keep the amount of energy received by the planet more stable over time. Earth also follows an almost circular orbit, so its distance from the Sun does not change dramatically throughout the year. If GJ 3378b had a highly elongated orbit, it might experience greater extremes of heat and cold as it moved closer to and farther from its host star. The current results do not indicate such an extreme variation. From the orbital period and the mass of the star, astronomers can calculate the planet's average distance. With a period of 21.45 days around a star only about 1/4 the mass of the Sun, GJ 3378b lies roughly 14.5 million kilometers from its host star. This distance was not measured with a ruler or seen in a photograph. It emerges from laws of motion that have been tested within the solar system for centuries. The same equations once used to determine the orbits of Mars, Jupiter, and comets are now used to calculate the distance of a world that cannot be seen. The planet's mass is also inferred from the force it exerts on the star. A more massive planet creates a larger wobble, and a closer orbit also increases the gravitational effect. Once the period, the mass of the host star, and the velocity amplitude are known, researchers can estimate the mass of the planet. But this method reveals only a minimum mass. The reason lies in the inclination of the orbit. If the planetary system is viewed nearly edge-on, most of the star's motion is directed toward and away from Earth, allowing us to measure almost all of its true velocity. If the orbit is seen closer to face-on, the star moves mainly sideways across the sky, and only a small part of its velocity appears in the Doppler measurements. GJ 3378b does not pass in front of its host star from Earth's point of view, so its orbit is not perfectly edge-on. We do not know its exact inclination, and therefore do not know its true mass. The value of about 2.3 Earth masses is the lowest mass consistent with the signal. Its actual mass may be greater. Even with this limitation, the new result changes how the planet is classified. The original estimate of more than 5 Earth masses placed it closer to mini-Neptunes surrounded by thick envelopes of gas. A minimum mass of 2.3 Earths moves it closer to the known population of rocky worlds. It all begins with a change in velocity no faster than a human step. There is no photograph of the planet, yet its gravity causes the star to move. No sound can cross the vacuum between star systems, yet the spectrum of light carries the rhythm of the wobble. No spacecraft has traveled to GJ 3378, yet telescopes can infer the length of the planet's year, the size of its orbit, and the minimum mass of the world circling the star. This is one of the most beautiful paradoxes of modern astronomy. A planet may be completely invisible, yet it cannot conceal its gravity. It does not need to emit light, pass in front of its star, or send any deliberate signal. Simply by existing and moving, it leaves an influence on the universe around it. The measurements from HPF, NADE, Carmenes, and Spirou do not show us the surface of GJ 3378b. They do not reveal whether the planet has clouds, mountains, or oceans. But they accomplish something more important at this early stage. They establish that the world truly exists and place the first limits on its nature. Over many years, the small star continued to wobble with a steady rhythm. Each instrument observed it through a different region of light, from observatories separated by thousands of kilometers across Earth. The data were imperfect, the measurements contained noise, and many nights of observation did not produce the results researchers had hoped for. But when all the evidence was placed side by side, a shared pattern began to emerge. About every 21.5 days, the star completes one cycle of its subtle motion. It moves slightly closer to us, gradually slows, then retreats before returning again. This wobble had been repeating long before humans possessed telescopes, and it will continue whether anyone is watching or not. GJ 3378b remains beyond our direct sight, but it is no longer entirely beyond our understanding. From a motion of only about 1.3 meters per second, astronomers have brought it out of the darkness of unknown worlds. The planet now has a measured orbital period, a minimum mass, and a relatively clear position within its star system. As the newer numbers replace the earlier results, GJ 3378b no longer resembles the massive mini-Neptune it was once imagined to be. It has become a lighter world, closer to the family of rocky planets, and therefore closer to the question humanity has always wanted to ask of distant points of light. Does it possess a true surface, an atmosphere, and conditions stable enough for water to exist? For many years, GJ 3378b has continued orbiting its star with the same steady rhythm, neither speeding up nor slowing down, and certainly not changing its mass, simply because humans began observing it with better instruments. Yet on maps of known exoplanets, this world has undergone a remarkable transformation. Once thought massive enough to carry a thick envelope of gas, like a smaller version of Neptune, it has gradually emerged as a candidate more closely related to rocky planets. The change did not occur in space, but in the numbers extracted from the light of its star. The original results suggested that GJ 3378b required about 24.73 days to complete one orbit. At the time, the signal also indicated a minimum mass of roughly 5.26 times that of Earth. This is not especially large when compared with giant planets. Jupiter is more than 300 times as massive as Earth, while Neptune has about 17 times Earth's mass. But in the range between Earth and Neptune, a difference of only a few Earth masses can lead a planet down a very different path of formation. A world 5 times more massive than Earth could still be composed mainly of rock and metal. Stronger gravity could compress its interior, producing a solid planet with a thick mantle and a large core. At that mass, however, the planet would also have had a greater chance of retaining hydrogen and helium from the primordial cloud of gas that gave birth to the star system. If radiation did not strip away that light gaseous envelope, it could surround the rocky interior, greatly increasing the planet's radius and hiding any solid surface beneath it. Worlds of this kind are often called mini-Neptunes. They are smaller than Neptune, but not necessarily similar to Earth. Beneath their thick atmospheres may lie layers of matter compressed under enormous pressure, where the idea of a clearly defined surface becomes difficult to apply. There may be no coastline where water meets rock, no thin layer of air resting just above solid ground, and no place where a person could imagine standing beneath a sky in the familiar way we do on Earth. With its original minimum mass of about 5.26 Earths, GJ 3378b appeared to lie near the transition between two families of worlds. It could have been a very large, rock-rich super-Earth, or a mini-Neptune with a substantial outer envelope of hydrogen and helium. Mass alone was not enough to distinguish between these possibilities, but it made the scenario of a planet with a thick, gaseous layer difficult to ignore. Then new data were added. Measurements collected over many years made the true period of the signal clearer. Instead of 24.73 days, GJ 3378b now appears to require only about 21.45 days to complete one orbit around its host star. At the same time, the amplitude of the star's wobble was revised downward, reducing the planet's estimated minimum mass from more than 5 Earths to about 2.3. This difference is far more significant than a few decimal places might suggest. GJ 3378b no longer appears to be a heavy world standing close to the boundary of the mini-Neptune population. With a minimum mass of only about 2.3 times that of Earth, the possibility that it is composed mainly of rock and metal becomes much more compelling. Its gravity would still be stronger than Earth's, but the planet may never have captured a thick primordial atmosphere, or that atmosphere may have been stripped away by radiation from the host star during its early history. A subtle change in the measured rhythm of the star's motion has moved the planet away from the image of an opaque gaseous sphere and closer to the possibility of a solid surface. There may be rocky plateaus, vast lowlands, or a fractured crust shaped by heat rising from the interior. The surface might instead be covered in ice, lava, or a deep global ocean. But before those images become too vivid in the imagination, it is important to remember that current data do not allow us to see any of these details. The first thing to understand is that the figure of 2.3 Earth masses is not the confirmed mass of GJ 3378b. It is the planet's minimum mass. This term is used because the radial velocity method measures only one part of the star's motion, the part directed toward or away from Earth. Imagine a person walking in a circle around a lamppost. If we stand level with the plane of that motion, the person sometimes approaches us and sometimes moves away, making the change in distance easy to see. But if we look down from almost directly above, the person moves mostly from side to side, while the distance between us changes very little. The true motion remains the same. Only the part directed toward us is different. A planet's orbit can also be tilted at many different angles. If GJ 3378b circles its host star in a plane viewed nearly edge-on from Earth, the star will wobble clearly toward us and then away. In that case, the measured radial velocity would represent nearly all of the star's true motion, and the value of 2.3 Earth masses might be fairly close to the planet's actual mass. If the orbital plane is tilted more strongly, most of the star's movement occurs sideways across the sky, instead of directly toward or away from Earth. The Doppler signal would then appear smaller, even though the planet itself might be more massive. Because the exact inclination is unknown, astronomers can only say that the mass cannot be lower than about 2.3 times that of Earth. It may be close to this value, but it could also be higher. In many planetary systems, a transit helps resolve part of this problem. When a planet crosses in front of its host star, the orbit must be viewed nearly edge-on. The inclination is then constrained quite tightly, allowing the mass inferred from radial velocity measurements to become more precise. A transit also causes the star's brightness to decrease slightly, making it possible to calculate the planet's size from the amount of light it blocks. GJ 3378b does not pass in front of its star from our point of view. It may still move through similar positions in space, but its orbital path is not aligned precisely enough with Earth to cover the stellar disk. Because there is no transit, the inclination remains unknown, and the planet's diameter has not been measured directly. The absence of a diameter creates an important limitation. Mass tells us how much material the planet contains. Size tells us how widely that material is spread through a volume. When these two values are combined, scientists can calculate the average density, one of the strongest clues to the composition of a world. Earth has a high density because it contains large amounts of rock and metal. Saturn is far more massive, yet its average density is low because most of its volume consists of hydrogen and helium. A planet with the same mass as GJ 3378b, but a small radius would have a high density, consistent with a rock-rich composition. If its radius were much larger, the density would be lower, making a thick gaseous envelope more plausible. Not knowing the radius is like knowing how much a box weighs without knowing its size. A small, heavy box may contain metal. A much larger box with the same weight may be filled with lighter material. From weight alone, it is difficult to determine exactly what lies inside. For this reason, the most careful conclusion is not that GJ 3378b has been confirmed as a rocky planet. What can be said is that the new minimum mass increases the likelihood that it belongs to a rock-rich class of worlds. This is an important change, but not the final answer. The term super-Earth must also be understood within similar limits. It often brings to mind a larger version of Earth, with more oceans, stronger gravity, and perhaps conditions more favorable to life. In astronomy, however, the term mainly describes a range of masses or sizes. A super-Earth could be a rocky planet hot enough for its surface to melt, a frozen world, a tidally locked planet, or a sphere surrounded by an atmosphere hundreds of times denser than Earth's. The word super does not mean better, and the word Earth does not guarantee a similar climate. It simply indicates that the planet is larger than Earth, but has not reached the size of Neptune-like worlds. Two planets both classified as super-Earths could differ from each other more than Earth differs from Venus. GJ 3378b now falls within this category. Its minimum mass is greater than Earth's, but still far below Neptune's. What makes this range especially interesting is that the solar system contains no typical planet within it. Beyond Earth, there is no world with 2, 3, or 5 times our planet's mass. The next step upward is Uranus and Neptune, which are much larger and have very different internal structures. As a result, humanity has no nearby example that can be compared directly with GJ 3378b. We understand how an Earth-sized rocky planet behaves, and we know what large gas and ice planets are like. But the region between these two groups contains many kinds of worlds that do not exist in the solar system. Exoplanets have shown that nature is not limited to the familiar patterns found around the Sunday. A planet with about 2.3 times Earth's mass might have a larger iron core, a thicker rocky mantle, and geological activity lasting for a longer period. Internal heat could keep the mantle moving slowly, supporting volcanism and reshaping the surface over time. If water exists, it might remain on the surface, beneath ice, or locked within minerals deep inside the planet. Another possibility is that the planet formed with an enormous amount of water. In that case, a rocky interior might be covered by an ocean deeper than any found on Earth. At great depths, intense pressure could compress water into unusual forms of ice even while temperatures remained high. Such a world might contain abundant water while lacking direct contact between the ocean and rock, something that could affect important chemical cycles. GJ 378b may also retain a surrounding layer of gas, though thinner than the envelope usually imagined around a mini-Neptune. Its atmosphere might consist mainly of carbon dioxide, nitrogen, water vapor, or a very different mixture. If the planet once possessed a light hydrogen envelope, radiation from the red dwarf may have stripped most of it away, leaving heavier gases closer to the surface. All of these scenarios are consistent with part of the available data, and none has been confirmed. The revised measurements only narrow the range, rule out some less likely confellities, and make others more compelling. Exoplanet science often advances in this way, not by seeing an entire world all at once, but by gradually removing layers of uncertainty. The revised period of about 21.45 days also defines the orbit of GJ 378b more clearly. From the time required to complete one orbit and the mass of the host star, researchers calculate that the planet lies at an average distance of about 0.097 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, nearly 150 million kilometers. The orbit of GJ 378b is therefore only about 1/10 as wide as Earth's orbit, placing the planet roughly 14.5 million kilometers from its host star. If that distance were placed within the solar system, the planet would orbit far inside Mercury's path. But GJ 378 is many times fainter than the Sun, so a compact orbit does not necessarily mean the planet's surface must glow like heated metal. It is the balance between a faint star and a close distance that allows GJ 378b to receive an amount of energy similar to what reaches Earth. The new model also suggests that the orbit may be more nearly circular than previously believed. A circular orbit does not automatically make a planet habitable, but it keeps the distance from the star from changing too much throughout the year. If the orbit were highly elongated, the planet could receive very different amounts of radiation as it moved between its closest and farthest points, producing extreme seasonal changes in temperature. Earth also travels along a nearly circular orbit, which is why changes in our distance from the Sun are not the main cause of the seasons. GJ 378b may receive a relatively stable amount of energy during each orbit, but its true climate would still depend on many unknown factors, from its rotation rate and atmosphere to the way heat is distributed across different regions. The revised orbital measurements therefore create a clearer picture, a lower mass planet moving along a shorter, possibly nearly circular orbit, receiving almost as much energy as Earth receives from the Sunday. These characteristics place GJ 378b among the more intriguing known worlds, but each one is still accompanied by an important gap in our knowledge. The lower mass increases the possibility of a solid surface, but the unknown orbital inclination means the planet's true mass may still be greater. Its orbit lies within the habitable zone, but no one knows whether the planet contains water. The amount of energy it receives is close to Earth's, yet its atmosphere could transform that same energy into a completely different environment. Venus provides the clearest reminder. It is close to Earth in size and mass, but its dense carbon dioxide atmosphere traps heat so effectively that the surface temperature rises above 460 degrees Celsius. Mars lies farther from the Sun and has an atmosphere too thin to retain much heat or keep liquid water stable on its surface today. The three rocky planets in our neighborhood have followed three very different climatic histories, even though they all orbit the same star. GJ 3378b may represent a fourth path, one that has no equivalent in the solar system. A planet larger than Earth and orbiting close to a red dwarf may retain an atmosphere more effectively because of its stronger gravity, while also enduring high-energy radiation over immense periods. The favorable and unfavorable factors do not simply cancel each other out. They act at the same time, creating a history that current models are only beginning to describe. A mass greater than Earth's could help the planet retain gas. Molecules attempting to escape into space would need to reach higher velocities to overcome its gravity. But if the host star releases enough ultraviolet radiation and X-rays, the upper atmosphere could be heated, expand outward, and gradually escape. A more massive world is not completely immune to this process. The planet's unknown size also affects its surface gravity. If GJ 3378b is only slightly larger than Earth, but has 2.3 times its mass, gravity at the surface could be considerably stronger. If its radius is much larger, because of a gaseous envelope or deep layers of water, gravity in the atmosphere may be closer to Earth's. Without a measured diameter, every estimate remains dependent on models. It is also unknown whether the planet's internal structure generates a magnetic field. On Earth, the motion of liquid iron within the core creates a magnetic field around the planet, helping deflect some of the charged particles arriving from the Sunday. A larger rocky planet might retain its internal heat for longer, but whether its core moves in a way that can sustain a lasting magnetic field would depend on its composition and cooling history. A magnetic field is not a perfect shield, nor is it the only condition required to preserve an atmosphere. Venus has almost no global magnetic field like Earth's, yet it retains an extremely dense atmosphere. Mars may have possessed a stronger magnetic field in the past, but today it is surrounded by only a thin layer of gas. These examples show that an atmosphere is shaped by planetary mass, temperature, radiation, geological activity, and time acting together. GJ 3378b, therefore, cannot be understood through a single number. Even so, revising its minimum mass from 5.26 to 2.3 Earth masses represents a turning point because it changes the relative likelihood of different scenarios. A hydrogen-rich mini-Neptune is no longer the most prominent possibility. A rocky planet with a thinner atmosphere has become more plausible, although it has not been confirmed. There is an enormous difference between saying that a world may have a rocky surface and declaring that it is another Earth. The first statement acknowledges the limits of the data. The second fills the unknown spaces with imagination. Science needs imagination to ask questions, but it also requires patience not to turn possibility into fact before observations support it. The image of a solid surface on GJ 3378b remains especially compelling. If the planet is truly rich in rock, it may possess geological structures shaped by stronger gravity and an internal thermal history unlike Earth's. Mountains may be limited in height by their own weight. Basins could be broad and deep. Volcanic activity, if it continues, may carry gases from the interior into the atmosphere and help maintain surface pressure over time. But the surface may also have been silent for a very long time. If the interior cooled, geological activity weakened, and the host star eroded the atmosphere, GJ 3378b may have become a barren rocky world. It would still lie within the habitable zone, according to its distance, and still receive an amount of energy similar to Earth's, but it would no longer possess a layer of gas thick enough to retain heat or sustain liquid water. Both opposing images remain compatible with the available data. One is a planet with a solid surface, an atmosphere, and slow geological cycles. The other is a dry sphere of rock with extreme differences between day and night, where every molecule of surface water disappeared billions of years ago. The revised measurements do not choose between them. They only show that the question is now more worthy of serious investigation. The changing understanding of GJ 3378b also shows how planetary labels can conceal considerable uncertainty. Super-Earth, rocky planet, and habitable zone are all useful terms, but each describes only one part of the world. None reveals what the sky looks like, what the surface temperature is, or whether life exists. Classifying a world as a super-Earth is only the beginning. Scientists still want to know its radius, density, atmospheric composition, reflectivity, temperature, geological activity, and the history of radiation from its host star. Each answer depends on a different observational method, another generation of telescopes, and sometimes decades of waiting. GJ 3378b currently resembles an object being weighed in the dark. We can sense its mass through the way it makes the star wobble, and we know how long it takes to complete an orbit and how far it lies from its host star. But its shape, size, and outer layers remain hidden. From the available data, we can construct many models, but we cannot yet see the real world behind them. Even so, the new measurements have accomplished something important. They have moved GJ 3378b closer to the family of rocky planets and brought questions about its surface, atmosphere, and water into sharper focus. A world once thought likely to be covered by a thick gaseous envelope may instead possess solid ground beneath the faint light of a red dwarf. At a distance of nearly 14.5 million kilometers from its host star, the planet completes each orbit in a little more than 3 weeks. Every orbit pulls the star slightly out of position, and from that motion, the numbers have gradually been revised. A shorter period, a lower mass, and a more circular orbit. None of these measurements reveals mountains, oceans, or clouds, but together they have changed the shape of the world in the human imagination. GJ 3378b may be a large rocky sphere with an atmosphere just thick enough to retain heat. It may once have possessed oceans and later lost them. Or beneath an atmosphere that remains too dense, there may be no surface resembling anything familiar to us. We cannot yet know, but possibilities involving rock and a thinner atmosphere are no longer far removed from the data. A rocky planet at the right distance is remarkable. But rock and distance alone do not create an ocean. For water to survive over immense spans of time, GJ 3378b would also need an almost invisible layer of protection, an atmosphere thick enough to retain warmth, but not so thick that it turns the world into a furnace, resilient enough to withstand radiation from the star, yet stable enough to prevent all its water from being driven into either ice or vapor. And it is this unseen layer of gas that will determine whether the new measurements describe only a rocky planet or whether they are bringing us closer to a world capable of sustaining conditions more favorable to life than anyone first imagined. At a distance of nearly 14.5 million kilometers from its small star, GJ 3378b completes one orbit in only about 21.45 Earth days. If a clock durable enough could be placed on that planet, each year would pass before a single month on Earth had come to an end. Red and infrared light from the host star continuously falls across a surface that has never been seen, delivering an estimated 91% of the energy Earth receives from the Sunday. That number is what makes GJ 3378b so remarkable. It is not so close to its star that it must obviously be scorching hot, nor is it so far away that it must certainly be frozen. Judging only by the amount of energy reaching the planet, this world lies near the region where water could exist in liquid form, at least according to the simplest models. That is also why it is often placed within the habitable zone of its host star. But the habitable zone is not a place where oceans appear simply because a planet enters it. It is more like a region with relatively favorable starting conditions than a confirmation of habitability. A house may stand in a mild climate, yet still have no roof, no doors, no water supply, and none of the conditions required for anyone to live there. The right address does not automatically create a suitable home for life. GJ 3378b occupies such a noteworthy address. Its distance from the host star allows it to receive an amount of energy not too different from Earth's, but whether the planet is truly warm depends on things we cannot yet see. An atmosphere may trap heat or allow it to escape. Clouds may reflect light back into space or hold warmth near the surface. Ice may make the planet brighter and colder, while dark oceans may absorb more energy. A change in only one of these factors could lead two planets receiving the same amount of radiation toward entirely different environments. The equilibrium temperature of GJ 3378b is estimated to be about 272 Kelvin, close to 31 degrees Fahrenheit or -1 degree Celsius. At first glance, this number seems to place the planet just below the freezing point of water. It easily brings to mind a cold but not completely frozen world, where seas might survive near the equator or beneath a thin layer of clouds. However, equilibrium temperature is not the planet's actual surface temperature. It is only an idealized calculation. It treats the planet as an object that receives energy from its star and releases heat back into space, then determines the temperature at which those two processes balance. The calculation usually assumes that the planet reflects a certain fraction of the incoming light and that heat is distributed in a relatively simple way. It does not know whether the surface is made of dark rock, bright ice, deep water, or a thick layer of clouds. It does not even know whether an atmosphere exists, much less which gases that atmosphere might contain. Earth shows how large the difference between equilibrium temperature and actual temperature can be. If we calculate only the energy received from the sun and ignore the warming effect of the atmosphere, Earth's equilibrium temperature is about -18 degrees Celsius, or roughly 0 degrees Fahrenheit. Yet the average temperature at the surface is considerably higher, around 15 degrees Celsius, or 59 degrees Fahrenheit. Most of that difference comes from the natural greenhouse effect, a process that retains part of the planet's heat through water vapor, carbon dioxide, and other gases in the atmosphere. Without the greenhouse effect, the Earth we know would be much colder. Surface water would struggle to remain liquid across broad regions, the oceans might freeze far more extensively, and the climate would be completely different. The greenhouse effect is therefore not inherently harmful. It is an essential part of what keeps our planet warm enough for liquid water. Problems arise only when that effect becomes too weak or too strong. Venus is an example of a world where heat retention has gone much further. The planet is nearly the same size as Earth, and on the scale of the solar system, its distance from the sun is not dramatically different. But its dense carbon dioxide atmosphere traps heat so efficiently that surface temperatures rise above 460 degrees Celsius, or about 860 degrees Fahrenheit. Clouds of sulfuric acid cover the entire planet, while the pressure near the surface is many times greater than what we experience on Earth. Venus is not hot simply because it lies closer to the Sunday. Distance plays an important role, but the atmosphere determines the final severity of the environment. A world receiving more energy than Earth does not necessarily have to become another Venus, but if it retains a thick layer of greenhouse gases and loses the processes that regulate its climate, its temperature may rise far beyond what its orbital distance alone would suggest. At the other extreme, Mars receives less energy than Earth and has a very thin atmosphere. Today, its average temperature is low. Liquid water cannot remain stable on the surface for long, and most of its water exists as ice or is trapped within the soil and rocks. Dry valleys, ancient river deltas, and minerals formed in water reveal that Mars once had a wetter past. But as the planet lost most of its atmosphere, the surface gradually became the cold desert now being explored by robotic rovers. The three rocky planets of the solar system tell three very different stories. Venus retains too much heat, Mars retains too little, and Earth lies between them, with an atmosphere and water cycle stable enough for oceans to survive through most of the planet's history. These differences cannot be explained by distance from the Sun alone. The same is true of GJ 3378b. Receiving about 91% of the energy that reaches Earth tells us only that the star provides heat within an interesting range. It does not reveal the temperatures of the day side, the night side, the poles, or the equator. It does not tell us whether there are clouds, rain, or snow. Nor does it reveal whether the planet has retained enough air to prevent water from immediately freezing or escaping into space as vapor. If GJ 3378b has no atmosphere, its surface may experience enormous differences in temperature. The illuminated side would absorb energy directly from the host star, while the dark side would rapidly lose heat into space. If the planet is tidally locked, one hemisphere may always face the star while the other remains in prolonged darkness. Air and oceans, if they exist, would play an important role in carrying heat between the two sides. Without them, the boundary between warmth and cold could become far more pronounced. Tidal locking often brings to mind an image of one half of a planet being scorched while the other remains permanently frozen. But reality may be more complicated. A sufficiently thick atmosphere could produce continuous winds that carry heat from the day side to the night side. An ocean could also redistribute warmth through currents, reducing the most extreme differences. In that case, the region near the boundary between day and night might maintain more moderate temperatures. If the atmosphere is too thin, heat transport will be weak. The dark side could become cold enough for some atmospheric gases to condense and freeze onto the surface, causing the atmosphere to grow even thinner. If the atmosphere is sufficiently dense but contains too many greenhouse gases, the day side could become far warmer than the simple equilibrium temperature suggests. The same amount of energy from the star could produce a frozen world, a temperate climate, or an intensely hot environment, depending on the layer of gas surrounding the planet. This makes the figure of 272 Kelvin both valuable and something that must be interpreted carefully. It shows that GJ 3378b does not occupy a location that is obviously too hot or too cold according to a basic model. But it is not a thermometer placed on the surface. No instrument there has measured the temperature of the rock or soil. No satellite has orbited the planet to map its clouds. That number is a starting point for climate models, not a final description of the climate itself. Temperature alone is also not enough for liquid water to exist. Surface pressure plays an equally important role. On Earth, water can remain as ice, liquid, and vapor because atmospheric pressure falls within a suitable range. If the pressure is too low, liquid water becomes unstable. It may boil at a low temperature or pass directly from ice into vapor without remaining long enough to form lakes or seas. This is what happens across most of the Martian surface today. Even when temperatures occasionally rise above the freezing point, the pressure is too low for liquid water to remain stable. A small amount may melt briefly, but it quickly evaporates or freezes again. For this reason, whenever a planet is said to have a temperature near the freezing point of water, the next question must always be how much pressure its atmosphere produces. For GJ 3378b, there is still no answer. Because the planet does not transit, starlight does not pass through its atmosphere in a way that can be easily measured from Earth. We do not know whether that layer of gas is thick or thin, whether its composition resembles the atmospheres of Earth, Venus, Mars, or something entirely different. We cannot even say with certainty that it still exists. If GJ 3378b has retained an atmosphere with moderate pressure, water vapor and greenhouse gases could raise the surface temperature above the equilibrium value. A modest amount of warming might allow liquid water to exist in some regions. If the atmosphere is much thicker, the planet could become warm enough for water to evaporate rapidly, moving it far away from the image of a mild and temperate world. A very thin atmosphere would lead to the opposite result. The surface could be colder, the contrast between day and night more severe, and any water that once existed could remain trapped as ice or gradually escape into space. Between these two extremes lies a wide range of intermediate states that climate models are still trying to describe. Water does not simply appear on a planet because the temperature allows it. It must come from somewhere, and it must survive the world's long history. During the formation of the star system, GJ 3378b may have been built from rock, metal, ice, and hydrogen-bearing compounds. The proportion of each material would depend on where the planet formed within the disk around the star and how it migrated to its present orbit. If it formed close to the host star, the higher early temperatures may have made it difficult for volatile materials, including water, to accumulate. The planet could still have received additional water from smaller bodies that struck it later. Asteroids, comets, or ice-rich fragments may have delivered water to the surface while the young planetary system was still chaotic. Some water may also have existed deep inside the planet. On Earth, minerals within the mantle can hold hydrogen and water within their structures. Volcanoes release water vapor along with many other gases, helping create or replenish the atmosphere over time. If GJ 3378b is a rocky planet that remains geologically active, similar processes may have taken place there. But just as water can be delivered, it can also be removed. Ultraviolet radiation from the star can break apart water molecules in the upper atmosphere. Lightweight hydrogen escapes into space more easily, while oxygen may react with the rocks or gradually be lost as well. If this process continues long enough, a planet that once held abundant water may become dry and barren. The early life of a red dwarf is especially important. Before settling into its present level of brightness, a young red dwarf may release intense energy for an extended period. A planet that lies within the habitable zone today may have received much more radiation in the past. If surface water evaporated into a steam-rich atmosphere, the greenhouse effect could have heated the planet further and pushed even more water into the upper atmosphere, where it would be more easily broken apart. A world whose present equilibrium temperature lies near the freezing point could still have lost its oceans long ago. A favorable location today cannot erase its early history. On the other hand, if the planet formed with a great deal of water, had enough mass to retain gases, and possessed internal processes capable of replenishing them, some of that water may still remain despite the host star's violent youth. GJ 3378b has a minimum mass of about 2.3 times that of Earth, so its gravity may help it retain atmospheric molecules more effectively than a smaller planet such as Mars. But gravity is not an absolute guarantee. The amount of high-energy radiation, the composition of the atmosphere, the temperature of its upper layers, and the presence or absence of a magnetic field can all influence how quickly gases are lost. What we currently possess are only indirect traces. The orbital period tells us that the planet circles its star in a little more than 3 weeks. Radial velocity measurements show that it has a mass of at least a few times that of Earth. The brightness of the host star and the planet's orbital distance allow us to calculate how much energy reaches it. From this, the equilibrium temperature can be estimated, but between those measurements and a single real drop of water, many unknown layers remain. There is no spectral evidence confirming water vapor. There are no images showing polar ice. There are no changes in brightness proving that oceans are reflecting light. There is no long-term climate record. Any picture of water on GJ 3378b must therefore remain a scenario, not a description. In one relatively favorable scenario, the planet may have retained a moderate atmosphere, thick enough to redistribute heat between the day side and the night side. Water released from the interior or preserved from the planet's formation could collect in low-lying regions. If the total amount of water were not too great, the The surface might contain shallow seas separated by rocky continents, where evaporation, clouds, and rainfall could occur beneath the faint light of the red dwarf. The light on such a world would differ from that on Earth. Its host star emits more energy in red and infrared wavelengths than the Sun, so plants, if any form of photosynthetic life had ever appeared, might need to adapt to a different spectrum. But this is a very distant speculation. Before considering the color of life, we do not yet know whether the planet has water or even an atmosphere. Another possibility is that GJ 3378b became an ice-covered world. If the atmosphere cannot provide enough warming, or if the surface reflects too much light, ice could spread across the planet. As the ice-covered area grows, the world would reflect more energy, causing temperatures to fall even further. This process could push the planet into a state in which most of the surface remains frozen. Even an ice-covered planet would not necessarily be completely without liquid water. Internal heat might preserve layers of water beneath the ice, much like the oceans suspected beneath the surfaces of icy moons in the solar system. But if the water were buried beneath a thick frozen shell, that environment would be very different from a planet with open seas and an active atmosphere. GJ 3378b could also be a dry world with a thin atmosphere. In that case, an equilibrium temperature near 272 Kelvin would not produce oceans. The surface might consist of rock, dust, and small deposits of ice in the coldest regions. Water that once existed may have been broken apart, lost to space, or trapped deep underground. If the planet has lost nearly all of its atmosphere, the landscape would be even harsher. The side facing the host star might warm beneath continuous light, while the dark side would become deeply cold. There would be no winds to carry heat, no clouds to reflect light, and no pressure high enough to support liquid water. Craters and rocky plains could remain almost unchanged for immense periods, altered only by impacts and fluctuations in temperature. Each scenario tells a different story, yet all of them can begin with the same numbers we observe today. An orbital distance of 0.097 astronomical units does not tell us whether the planet has oceans. Receiving 0.91 times Earth's radiation does not reveal its climate. An equilibrium temperature of 272 Kelvin does not tell us the true temperature at the surface. The habitable zone does only one very specific thing. It identifies the range around a star where a planet with a suitable atmosphere could maintain liquid water on its surface. The two most important words in that definition are could and suitable. If the atmosphere is not appropriate, even an ideal location is not enough. The boundaries of this zone are not sharp lines. Different models can place them slightly differently, depending on assumptions about clouds, greenhouse gases, pressure, and the type of star. A planet near the inner edge may be too hot in one model, but still able to retain water in another. A planet near the outer edge may require more carbon dioxide to avoid freezing. Around red dwarfs, the spectrum of starlight also creates important differences. Ice and snow absorb more red and infrared light than they do the visible light produced by the sun. So the relationship between ice and temperature may not work exactly as it does on Earth. Clouds may also respond differently to the unusual distribution of heat on a tidally locked planet. Atmospheric currents could gather clouds over the region that always faces the host star, where they would reflect part of the incoming energy and help prevent the surface from becoming excessively hot. Climate models suggest that some planets orbiting red dwarfs could maintain temperate conditions even if they are tidally locked, provided their atmospheres are thick enough to transport heat. But these results cannot be applied directly to GJ 3378b when its atmospheric pressure, composition, and true rotation rate remain unknown. They show only that tidal locking does not necessarily bring an end to the possibility of liquid water. Nor can we assume that receiving less energy than Earth automatically makes GJ 3378b colder than Earth. A dense atmosphere could raise the temperature considerably. In contrast, an ice-covered surface, and a thin atmosphere could make it far colder. The invisible conditions surrounding the planet are what transform energy from the star into a specific climate. On Earth, the oceans absorb heat during the day and through the summer, then release it slowly at night and during the winter. Water can store a great deal of thermal energy, helping to reduce changes in temperature. Ocean currents also carry energy from the equator toward higher latitudes, making the global climate more moderate. If GJ 3378b has oceans, water could play a similar role, especially by transporting heat from the day side to the night side. But the shapes of its continents, the depth of its seas, the speed of its winds, and the planet's rotation would create currents unlike those on Earth. A short year does not necessarily determine the rotation rate, particularly if the planet has become tidally locked to its star. Clouds are another difficult factor to predict. Low, thick clouds generally reflect light and cool the surface below, while high clouds can trap heat emitted by the planet and create a warming effect. On a world with one side permanently facing the star, clouds might gather over the most intensely illuminated region and form a natural shield. But if the atmosphere contains too much water vapor, that vapor would also act as a powerful greenhouse gas and warm the planet. The balance among these processes could shift over millions of years. Volcanoes add carbon dioxide to the atmosphere. Rainwater and chemical reactions with rock can remove some of that carbon dioxide from the air. On Earth, the long-term carbon cycle helps regulate the climate over geological time. No one knows whether GJ 3378b has continents, rainfall, plate tectonics, or any similar mechanism. A larger planet may retain its internal heat for longer, allowing volcanism and geological activity to continue over immense periods. This could help replenish an atmosphere after part of it had been lost. But excessive volcanic activity could also release large amounts of greenhouse gases and drive the climate toward more extreme conditions. The same process could both sustain an atmosphere and push it toward a hostile state. Water, atmosphere, and rock do not exist in isolation. They exchange material through rain, rivers, oceans, volcanoes, and chemical reactions. A planet's climate is the result of this entire network, guided by the energy of its star, but never determined by that energy alone. For now, GJ 3378b has revealed only the opening part of its story. Its star provides nearly enough warmth in a range familiar to Earth. The planet's mass means that retaining an atmosphere is not entirely beyond possibility. Its orbit appears relatively stable and lies within a noteworthy region around its host star. Everything else remains hidden. There is no evidence of oceans, no evidence of ice, no evidence of water vapor, and no evidence showing whether the surface is warmer or colder than the equilibrium temperature. Images of clouds, rain, and seas are only ways for models to help us consider the different possibilities. This caution does not make GJ 3378b any less fascinating. On the contrary, it reveals why the planet is such an important scientific target. If everything were already known, there would be little reason to direct future telescopes toward it. The space between a world occupying the right location and a world that truly has water is where the largest questions remain. One day, if the planet's light can be separated from the glare of its host star, astronomers may search for signs of water vapor, carbon dioxide, or other gases. Changes in heat along its orbit could reveal how the surface distributes energy. Reflected light might offer clues to clouds, ice, or oceans. For now, however, GJ 3378b appears only as a subtle gravitational pull carried within the light of its star. At a distance of 25 light-years, the planet continues to receive an almost constant flow of energy. If oceans exist, that light is falling across waters that no one has ever seen. If there is ice, it is reflecting part of the energy back into space. If the surface is dry, rock is still absorbing and releasing heat across different regions. And if the atmosphere has vanished, there may be almost nothing above the ground to hold on to warmth. None of these possibilities can be chosen from the number 272 Kelvin alone. The equilibrium temperature tells us only that the planet lies near an intriguing threshold. It opens the door to the question of water, but it does not carry us through that door. GJ 3378b may never have had water. It may once have possessed oceans and lost them while its host star was still young. Or some amount of water may remain beneath ice, within the mantle, or on the surface. Each possibility depends on a history that current observations cannot yet fully reconstruct. The habitable zone should therefore be understood as a region of investigation, not as confirmation of a habitable world. It helps scientists identify planets worthy of closer study, places where the heat from the star does not immediately rule out liquid water. After that, the atmosphere, planetary mass, history of the host star, and composition of the world determine the true story. GJ 3378b has passed that first test. It lies where the amount of energy is not far from what Earth receives. It may be rocky, and it may be massive enough to retain a layer of gas. But the word may still stands before every image of oceans, rain, and sky. Far away, another short year continues to pass every 21.45 days. The small star sends its light toward the planet across a distance of 0.097 astronomical units. That energy is almost enough to bring water into the question, but not enough to provide the answer. The star offers an amount of warmth that may be nearly suitable, yet that same star may once have released radiation, powerful enough to evaporate water, break apart molecules in the atmosphere, and gradually draw them into space. A place capable of retaining water may also be a place that lost it long ago. Between those possibilities lies an almost invisible layer of protection. The atmosphere that will determine whether GJ 3378b is a world capable of sustaining oceans, a silent planet of ice, or only a sphere of rock orbiting beneath the red light of a star that once stripped away everything water needed to survive on the surface. GJ 3378b lies at a distance that is nearly ideal for receiving an amount of heat not too different from what reaches Earth. Its compact orbit helps protect the planet from the deep cold that might engulf a world traveling too far from its host star, yet that same closeness places it in an environment where visible light is only the gentlest part of what the star emits. Along with warmth, the star sends ultraviolet radiation, X-rays, and streams of charged particles toward the planet, all of which can affect an atmosphere over immense spans of time. This is the familiar paradox of planets orbiting red dwarfs. A small, faint star cannot warm distant worlds the way the sun does. To receive enough energy, a planet must move much closer, sometimes many times closer than Mercury is to the Sunday. At that distance, it may occupy a region where liquid water is theoretically possible, while also facing the harsher aspects of its star from very close range. The light visible to the human eye represents only part of the energy a star releases. Beyond the familiar range of visible light lie ultraviolet radiation and X-rays, wavelengths that carry far more energy. They do not necessarily heat the surface in the same way sunlight warms the ground, but they can strongly affect the upper atmosphere, where the gas is thinner and molecules have less protection. When high-energy radiation enters the upper atmosphere, it transfers energy to atoms and molecules. Some molecules are broken apart, some atoms lose electrons and become ions, and the uppermost layers of gas heat up and expand. If the temperature rises high enough, the lightest particles may move fast enough to escape the planet's gravity. This process does not have to occur in a single dramatic event. A planet does not need to lose its atmosphere all at once during one enormous flare. Gas can escape in tiny amounts, day after day and year after year. Each loss may seem almost insignificant, but over hundreds of millions or billions of years, the total can completely transform the surface. Imagine a lake that is not drained in a single night, but loses water one drop at a time through a very small crack. For a few days, the water level barely changes. After many years, the lake bed begins to appear. A planetary atmosphere can decline in the same gradual way, so slowly that there may be no clear moment when a world with air becomes a nearly barren one. Light molecules, such as hydrogen, escape most easily. This is especially important for water because every water molecule contains 2 hydrogen atoms. Ultraviolet radiation can break apart water vapor in the upper atmosphere, freeing hydrogen to drift gradually into space. The remaining oxygen may react with rocks, be removed by other processes, or accumulate in the atmosphere, depending on the conditions of the planet. A world that once had water is therefore not guaranteed to keep it forever. If water vapor is continually carried into the upper atmosphere, hydrogen may slowly escape, reducing the planet's total supply of water over time. The planet may lose not only its atmosphere, but also the very material needed to form oceans. Red dwarfs make this story more complicated because their youth often lasts for a long time. A star like the Sun settles into relative stability fairly quickly after it forms, but a red dwarf may take much longer to reach a quieter state. During that period, it can be brighter than it will be later and may release significant amounts of high-energy radiation. Today, GJ 3378b receives nearly the same amount of energy that Earth receives from the Sun, but its present location does not tell the whole story. When the host star was young, the planet may have received much more energy. Its surface may then have been hotter, water may have evaporated more easily, and the upper atmosphere may have been exposed to stronger ultraviolet radiation and X-rays. If GJ 3378b possessed oceans during its early history, that water may have entered the atmosphere as vapor. A thick layer of water vapor would trap heat efficiently, warming the surface further and causing even more water to evaporate. As the vapor rose, the molecules could be broken apart and the hydrogen gradually lost to space. Given enough time, the oceans might have shrunk or disappeared, even if the planet later entered a temperature range that appeared more favorable. No one knows whether this process actually occurred on GJ 3378b. We have no direct record of the star's youth, no data revealing the planet's original supply of water, and no knowledge of how thick its atmosphere may once have been. Models show only that this is a possible path, not a confirmed history. In addition to electromagnetic radiation, the star also releases streams of charged particles, commonly known as stellar wind. The Sun continuously sends the solar wind through the solar system as well. When magnetic activity becomes intense, eruptions can launch large amounts of plasma into space, where they collide with the magnetic fields and atmospheres of planets. Around an active red dwarf, the stellar wind may be denser and more severe at close orbital distances. Charged particles strike the upper atmosphere, transfer energy, push ions away from the planet, or create extended streams of escaping gas. The exact effect depends on the planet's magnetic field, atmospheric composition, mass, size, and distance from the host star. A magnetic field is often imagined as a shield, but the reality is more complicated. On Earth, the magnetic field deflects many charged particles from the Sun and guides some of them toward the polar regions, where they produce auroras. This shield helps protect the atmosphere, but it does not stop every form of atmospheric escape. A planet without a global magnetic field does not necessarily lose its entire atmosphere immediately. Venus has almost no strong internal magnetic field like Earth's, yet it still retains an extremely dense atmosphere. Mars, by contrast, is smaller, has weaker gravity, and has lost most of its ancient atmosphere. A planet's ability to retain gas is the result of many factors acting together and cannot be determined solely by whether it has a magnetic field. The mass of GJ 3378b may work in its favor. With a minimum mass of about 2.3 times that of Earth, the planet may have stronger gravity, requiring gas molecules to reach higher speeds before they can escape. If its radius is not too large, the gravity near the surface could help it retain an atmosphere more effectively than a smaller world such as Mars. However, its true mass and size have not yet been fully determined. If the planet has a large radius because it is surrounded by a thick envelope of gas, the upper atmosphere may extend farther outward and become more exposed to radiation. If the planet is compact, dense, and rich in rock, gravity near the surface may be stronger. Without knowing the radius, any precise calculation of atmospheric loss remains highly uncertain. Researchers have used models to estimate the total amount of high-energy X-ray and ultraviolet radiation that GJ 3378b may have received over its history. The results suggest that the accumulated exposure could be around 48 times greater than the corresponding amount Earth has received. That number may sound large enough to conclude that the planet's atmosphere must have been stripped away, but its true meaning is far more cautious. This is not a measurement taken directly at GJ 3378b. No instrument has orbited the planet and recorded X-rays over billions of years. The estimate of roughly 48 times Earth's exposure is built from models of the star's age, its high-energy brightness, the evolution of red dwarfs, and the planet's orbital distance. Each part carries its own uncertainty. The radiation history of a star cannot be read like a temperature record from a weather station. Scientists must observe the star as it is today, compare it with similar stars of different ages, and then construct the most likely path of its evolution. GJ 3378 may once have been more active or less active than the average assumed by the model. Even if the total high-energy radiation exactly matches the estimate, it still does not reveal how much atmosphere was lost. A planet that formed with a thick atmosphere could lose most of it and still retain a substantial layer. A planet that began with only a thin atmosphere might become nearly airless much more quickly. Water, carbon dioxide, nitrogen, hydrogen, and helium also respond differently to atmospheric escape. Geological activity may also replenish gases from the planet's interior. Volcanoes release water vapor, carbon dioxide, sulfur compounds, and many other materials. If GJ 3378b has retained enough internal heat, outgassing from the mantle may have replaced part of what the star removed. In that case, the atmosphere would not be a fixed reservoir, but the result of a balance between loss and renewal. A world can have its atmosphere eroded from above while volcanoes rebuild it from below. If replenishment occurs faster than loss, the atmosphere may survive. If the star removes gas more quickly than the planet can replace it, the atmosphere will gradually thin. Over time, that balance may shift as the host star becomes quieter and geological activity begins to decline. This condition can be imagined as a shoreline, where land and ocean meet along a boundary that is never entirely still. On one side are planets that retain thick atmospheres, on the other are worlds that have lost nearly all of their air. Between them lies a transition sometimes described by astronomers as the cosmic shoreline. The name is more than a poetic image. When planets and moons in the solar system are compared, worlds that receive more radiation or have weaker gravity generally find it more difficult to retain atmospheres. Earth, Venus, and Titan lie on the side with substantial atmospheres. Mercury, the Moon, and many smaller bodies lie on the nearly airless side. Mars appears as a world that once had a thicker atmosphere, but lost most of it over time. This shoreline does not depend simply on distance from a star. Planetary mass pulls a world toward the atmospheric side, while radiation and stellar wind push it toward atmospheric loss. A larger planet may endure a harsher environment. A smaller world must remain in a quieter region if it is to preserve its air for a long time. GJ 3378b appears to lie somewhere near that boundary. Its mass is large enough that the possibility of retaining an atmosphere cannot be dismissed, but its close orbit around a red dwarf, together with its history of high-energy radiation, places considerable pressure on its upper atmosphere. Current models do not place the planet with certainty on the atmospheric side, nor do they clearly identify it as a completely barren world. This makes GJ 3378b more scientifically valuable than a planet whose answer is already clear. If it has retained an atmosphere, scientists will gain evidence that a super-Earth close to a red dwarf can survive the star's active youth. If its atmosphere has been lost, the planet will help reveal the limits that radiation may place on habitability around the most common type of star in the galaxy. The image of a cosmic shoreline also reminds us that the boundary may not be sharp. On Earth, tides move the shoreline from hour to hour. Storms carry sand away, currents deposit it elsewhere, and sea level changes over time. In space, atmospheres can also grow thicker, become thinner. Radiation is absorbed in the upper layers without causing all the gas to escape. As the star gradually settles into a quieter state, the rate of atmospheric loss declines. In this scenario, GJ 3378b still possesses an atmosphere thick enough to create meaningful surface pressure. Carbon dioxide, water vapor, or other greenhouse gases retain part of the planet's heat, raising the true temperature above the equilibrium value of nearly 272 Kelvin. Winds redistribute energy between the day side and the night side, reducing extreme contrasts if the planet is tidally locked. Water, if it has survived, may exist in liquid form in certain regions. Areas receiving more heat could contain seas or lakes, while ice accumulates in darker or higher regions. The ocean and atmosphere would transport heat together, creating a climate system very different from Earth's, but not necessarily completely hostile. A surviving atmosphere could also protect the surface from some high-energy radiation. The upper layers of gas would absorb ultraviolet radiation and X-rays, while chemical reactions might create additional protective layers depending on the atmospheric composition. The surface would then be shielded from direct exposure to the full space environment. But even this favorable scenario would not mean that life exists. The atmosphere could be too thick, too rich in carbon dioxide, or filled with unsuitable compounds. Water might lie beneath deep ice or remain locked inside minerals. The planet could retain air while still having surface temperatures, pressures, and chemistry very different from anything familiar. The opposite scenario begins during the star's young and highly active phase. Radiation causes water to evaporate, breaks molecules apart, and draws hydrogen into space. Stellar wind repeatedly strikes the upper atmosphere, removing ions and gradually thinning the layer of gas. The planet may once have had a denser sky, but each passing million years carried away another small part of it. As the atmosphere thins, its ability to retain and redistribute heat declines. Liquid water becomes more difficult to sustain. The night side freezes, while the day side warms and then loses heat more rapidly because the remaining air is no longer strong enough to carry energy around the planet. If the pressure falls too low, surface water may evaporate or sublimate before being broken apart and lost. Eventually, GJ 3378b may be left with a dry, rocky surface. Basins that once held water, if they ever existed, would become dust-covered depressions. Volcanoes might continue releasing small amounts of gas, but not enough to rebuild the atmosphere before the star removes it again. Day would never end on the side permanently facing the star, while the opposite hemisphere would remain in prolonged cold darkness. Such a world would still lie within the habitable zone according to its orbit. It would still receive about 91% of the energy Earth receives. Its equilibrium temperature could still be listed as nearly 272 Kelvin. But those numbers cannot create oceans without pressure, cannot produce rain without water vapor, and cannot restore an atmosphere that has already been lost. This is why location is no longer the most important question. Astronomers already know where GJ 3378b lies, how long it takes to orbit its star, and approximately how much energy it receives. What now determines the nature of the planet is whether a layer of gas still surrounds it. Between these two opposing scenarios lies a wide range of intermediate states. The planet may retain a very thin atmosphere, somewhat like Mars but slightly denser. It may have lost its original hydrogen and helium while preserving carbon dioxide, nitrogen, and water vapor released by volcanoes. It is also possible that the atmosphere remains mainly on the day side or partially freezes onto the night side. The composition of the atmosphere may have changed dramatically over time. Oxygen produced by the breakdown of water would not necessarily indicate life because it could accumulate through purely chemical processes. Carbon monoxide, carbon dioxide, and water vapor might reflect the balance among volcanism, radiation, and the surface. No single molecule could easily tell the entire story. The flares of red dwarfs also need to be viewed in proper perspective. They can be powerful and have significant effects, but GJ 3378 should not be imagined as a star erupting continuously without pause. Not every red dwarf behaves in the same way, and the level of activity changes with age, rotation rate, and magnetic structure. A flare may cause ultraviolet radiation to rise sharply for a short time, but a thick atmosphere can absorb much of that energy in its upper layers. The long-term effect depends on the frequency and intensity of the flares, the star's total radiation history, and the planet's ability to recover. A single event is rarely enough to determine the fate of an entire world. The present activity of GJ 3378 and its past are still not completely understood. Spectroscopic measurements can search for signs of magnetic activity, while its current X-ray emission can be observed with space telescopes. But what happened billions of years ago can only be inferred through models and comparisons with similar stars. This uncertainty does not reduce the scientific value of the estimate of 48 times Earth's exposure. It simply places the number in its proper context. It suggests that GJ 3378b has existed in a more difficult environment than Earth, but it is not direct evidence that the planet has lost all of its atmosphere. Models of atmospheric escape must often make assumptions about how efficiently radiation is converted into the motion of gas. The temperature of the upper atmosphere, its molecular composition, and the amount of magnetic shielding. A change in only one of these assumptions can lead to a very different estimate of how much gas has been lost. A planet that began with an atmosphere hundreds of times more massive than Earth's could suffer enormous losses and still retain a substantial layer. A planet that began nearly airless would have very little to lose. The history of impacts may also have changed the outcome. Large objects striking the planet could have blasted away part of its atmosphere, but they might also have delivered additional water and volatile materials. During the chaotic early stages of the system, GJ 3378b may have both lost and gained matter through many separate events. The planet's core and mantle would continue to play important roles after the era of major impacts had ended. A hot core might sustain a magnetic field. An active mantle could support volcanism and release new gases. Tectonic activity, if it exists, might carry carbon into the interior and later return it to the atmosphere, helping prevent the climate from drifting completely toward an extreme of heat or cold. There is currently no evidence showing whether GJ 3378b has plate tectonics. Even among the rocky planets of the solar system, Earth is the only world known to possess an extensive system of active plates. Venus is nearly the same size, yet its surface has evolved in a very different way. A super-Earth could be more active, less active, or governed by a mechanism entirely unfamiliar to us. Every factor leads back to the same question. Does an atmosphere exist there today? If it does, how thick is it? If it does not, what traces might remain on the surface to reveal whether the planet once had water? These questions are more important than simply establishing that the planet lies within the habitable zone. A world may orbit at the right distance and still lack every condition required for habitability. In contrast, a planet slightly beyond the theoretical boundary might retain water because of an unusual atmosphere. The habitable zone helps identify where to search, but the atmosphere determines whether surface conditions truly enter a suitable range. On GJ 3378b, that layer of gas may be only a few dozen kilometers thick, yet it could represent the entire difference between ocean and rock, wind and vacuum, relatively stable temperatures, and extreme variation. Its mass would be almost negligible compared with the planet as a whole, but it would control the light, heat, and pressure where the surface meets space. Earth's atmosphere is also only a very thin layer when seen from a distance. In images taken from space, it appears as a narrow blue line surrounding the planet. Despite its fragility, that layer creates clouds, transports heat, protects the surface, and allows the oceans to exist. Remove it, and Earth would retain almost all of its mass, yet the familiar environment would disappear. GJ 3378b may still carry a similarly thin outline around itself, though its composition and color could be completely different. Or that outline may have faded into space long ago. Radial velocity measurements cannot distinguish between these possibilities, because the planet's gravitational pull would remain almost unchanged whether the atmosphere survived or vanished. An atmosphere as massive as Earth still represents only a tiny fraction of a planet's total mass. If it disappeared, GJ 3378b would continue pulling on its star in almost exactly the same rhythm. Instruments that measure the orbit can determine the planet's mass and period, but they cannot directly sense the thin layer of material that controls its entire climate. To learn whether a atmosphere exists, astronomers must search for its imprint in light. When a planet passes in front of its star, some of the starlight travels through the layer of gas around the planet's edge. Different molecules absorb different wavelengths, leaving chemical fingerprints in the spectrum. Water vapor has its own absorption bands. Carbon dioxide, methane, oxygen, and many other gases leave different patterns as well. By comparing the starlight before, during, and after a transit, scientists can isolate the extremely faint signal belonging to the atmosphere. This method has already begun to reveal the composition of many exoplanets, especially large worlds with thick atmospheres. The signal is much weaker for small rocky planets, but a small host star can offer an advantage because the planet blocks a larger fraction of its light. GJ 3378b, however, does not pass in front of its star from Earth's point of view. Its orbit is tilted just enough for the planet to move above or below the stellar disk in the sky. No transit allows the light of GJ 3378 to pass through the planet's atmosphere before reaching our telescopes. As a result, the most important layer of gas remains beyond the reach of the most favorable observational method available today. GJ 3378b may have preserved an atmosphere through billions of years of radiation, or it may now possess only a silent rocky surface. Its star has supplied nearly enough warmth for water, yet it may also have removed the protective layer needed to keep that water from escaping. The central question is no longer where the planet is orbiting. Its path has been measured, its period has been determined, and the amount of energy it receives has been estimated. What remains missing is evidence of the invisible boundary surrounding this world, the thin layer of matter between the surface and space where the fate of its water may have been decided billions of years ago. To discover whether that atmosphere truly exists, astronomers need to observe light passing through it. But from Earth's point of view, GJ 3378b never crosses in front of its star. For many years, the light of GJ 3378 has been recorded with instruments sensitive enough to detect a stellar motion, no faster than a person walking. From that tiny shift, astronomers identified a planet orbiting the star, measured the length of its orbit, and placed the first limits on the mass of the invisible world. But light can reveal the gravitational influence of a planet, while still telling us nothing about what lies beneath its atmosphere. and in the case of GJ 3378b, most of the most important questions remain beyond the reach of current observations. From 2019 through early 2024, the TESS Space Telescope observed GJ 3378 during 4 separate observing campaigns. TESS was not designed to capture detailed images of the surfaces of distant planets. Instead, it monitors the brightness of stars over long periods, searching for regular dips in light that occur when a planet passes in front of them. If its orbit were aligned with our line of sight from Earth, GJ 3378b would block a very small portion of the star during each orbit. The resulting dip in brightness might be slight, but if it repeated every 21.45 days, it would create a pattern clear enough for algorithms to identify. The research team analyzed more than 57,000 measurements of GJ 3378's brightness. Each point recorded the amount of light arriving from the star at a particular moment. When tens of thousands of these points are arranged in sequence, they form a long light curve in which small dips may emerge from instrumental noise, stellar activity, and other natural variations. But within that data set, no decrease in brightness matched the signature of a planet crossing the stellar disk at the known period. GJ 3378b exists, and its gravitational pull has been measured, but from Earth's perspective, its orbit is tilted just enough that the planet does not pass in front of its host star. It may travel just above or below the star in the sky, missing the bright edge by only a small distance. In three-dimensional space, the planet continues to complete its regular orbits as always, but the geometry of the system does not allow us to see its shadow. The absence of a transit prevents astronomers from using several of the most effective observational methods. When a planet passes in front of its star, its solid body, or thick atmosphere, blocks some of the light, while a small amount of starlight travels through the atmosphere around the planet's edge. Along the way, molecules in that atmosphere absorb specific wavelengths. Water vapor leaves one set of signatures. Carbon dioxide, methane, carbon monoxide, and many other molecules produce different absorption patterns. If the signal is strong enough, astronomers can compare the star's light before and during the transit, then isolate the tiny fraction that passed through the planet's atmosphere. This method is commonly known as transmission spectroscopy. It cannot show clouds drifting across the sky or oceans stretching over the surface, but it can provide the first clues about the composition of the gases surrounding a distant world. For GJ 3378b, this favorable observational path is closed. No starlight passes through the planet's atmosphere along the precise direction needed to reach telescopes on Earth. If an atmosphere exists, it remains outside the line of sight required for transmission spectroscopy. This does not mean that the planet has no atmosphere. It means only that the geometry of the system prevents us from testing for one through the most accessible method. A planet could possess a thick atmosphere, clouds, and even complex weather patterns without ever producing a transit from the solar system's point of view. The absence of a transit also keeps another fundamental property hidden: the planet's radius. When a world blocks its host star, the depth of the dip reveals how much of the star's surface area has been covered. If the size of the star is known, researchers can then calculate the diameter of the planet. GJ 3378b does not allow that measurement. We know that its gravity is strong enough to make the star wobble, which gives it a minimum mass of about 2.3 times that of Earth. But an object with 2.3 Earth masses could be compressed into a relatively small sphere or spread across a larger volume if it carries a substantial amount of gas or water. Without a radius, its average density cannot be calculated. Without density, distinguishing a mostly rocky planet from a world with a thick gaseous envelope still depends more on models and probabilities than on direct measurement. A rocky planet usually has a high density because most of its material consists of silicates and metals. A mini-Neptune may contain a rocky core surrounded by hydrogen, helium, or other lighter materials, greatly increasing its radius without requiring a proportional increase in mass. A water-rich world might fall somewhere in between, with a density lower than that of a dry, rocky planet but higher than that of a planet with a thick primordial atmosphere. GJ 3378b could belong to any of these groups. Its revised mass makes a rocky composition more plausible, but without a measured size, its true structure remains hidden. Even if the radius were known, we still would not be able to see the surface. A planet with a density consistent with rock could still be covered by deep oceans, ice, or a thick layer of clouds. Density narrows the possibilities, but it does not create a map. To go further, astronomers would need to separate the light of the planet itself from the light of the star. This is the goal of direct imaging, one of the most difficult challenges in exoplanet research. From a distance of 25 light-years, GJ 3378, and its planet appears so close together in the sky that the separation between them is extremely small. The star is millions of times brighter than the planet, depending on the wavelength and the nature of the planet's surface. It is like trying to see a faint speck of dust resting beside a powerful headlight from very far away. Even if a telescope collects enough light, optical effects still cause the starlight to spread across the detector. Diffraction rings and tiny imperfections in the mirrors can create false points of light that easily overwhelm the signal from the planet. To overcome this problem, direct imaging instruments use several techniques at once. One component may block part of the central light from the host star. Adaptive optic systems continuously adjust the mirrors to compensate for turbulence in Earth's atmosphere. Image processing algorithms then attempt to separate structures created by the instrument from a real point of light moving along an orbit. Next-generation ground-based telescopes, such as the Giant Magellan Telescope and the Extremely Large Telescope, are being built with mirrors far larger than those of most observatories operating today. A larger mirror not only gathers more light, but also improves the ability to distinguish two sources that appear very close together in the sky. These observatories may combine their enormous mirrors with advanced adaptive optics, high-resolution spectrographs, and instruments designed to suppress starlight. Under favorable conditions, they could move closer to detecting thermal emission or reflected light from small planets orbiting nearby stars. Even so, GJ 3378b remains a difficult target. Its orbit of about 0.097 astronomical units places it very close to its host star. Although the system is only about 25 light-years from Earth, the angular separation between the planet and the star is still extremely small. An instrument may be sensitive enough to detect the planet's light, yet lack the resolution needed to separate it from the glare of the star. Contrast is another major obstacle. A rocky planet does not shine strongly on its own like a star. It only reflects a fraction of the light it receives or emits faint thermal radiation. If the surface is dark, the planet has few clouds, or only part of its illuminated side is visible. The signal becomes even weaker. Future space telescopes, designed specifically to search for potentially habitable worlds, are expected to reduce some of these difficulties. Beyond Earth's atmosphere, instruments do not have to contend with air turbulence, allowing images to remain more stable. A telescope equipped with a sufficiently precise coronagraph or a separate starshade flying in formation through space could block the starlight before it enters the optical system. If the light of GJ 3378b is ever successfully separated from its star, astronomers may be able to analyze the planet's spectrum directly. They would no longer need to wait for starlight to pass through the atmosphere during a transit. Light reflected from clouds and the surface, or thermal radiation emitted by the planet itself, could carry the signatures of molecules in its atmosphere. A sufficiently detailed spectrum might reveal whether carbon dioxide is present, whether water vapor leaves a detectable trace, and whether the atmosphere contains methane or other compounds. Changes in brightness over time could suggest that the planet is rotating, that different regions are brighter or darker, or that its clouds are changing. But the distance between detecting a faint signal and confirming the presence of oceans or life is enormous. Water vapor can exist in an atmosphere without forming surface oceans. Methane can be produced by geological processes rather than living organisms. Oxygen can also accumulate through processes unrelated to life, especially on a planet exposed to intense radiation. Every potential sign must be interpreted within the full context of the planet and its host star. Atmospheric composition, temperature, pressure, stellar activity, and the history of atmospheric escape must all be considered together. A single molecule is rarely enough to tell the entire story. Before searching for such subtle biological signatures, astronomers must complete a more fundamental task: mapping the worlds that exist around stars near the solar system. Our astronomical neighborhood includes far more than the stars visible to the naked eye. It contains hundreds of faint red dwarfs, many of which may host small planets that have not yet been discovered. Some systems have been monitored in great detail, while others have only a few years of data, leaving longer period orbits still hidden. Radial velocity surveys must continue measuring stars over many years to search for planets with longer orbital periods. TESS and other transit observatories can detect worlds whose orbits happen to be aligned with our line of sight. Extremely precise astrometric measurements can reveal the sideways motion of a star across the sky as it is pulled by an orbiting planet. When these methods are combined, a map gradually begins to take shape. On that map, each planet is marked by its mass, orbital period, distance from its host star, and the amount of energy it receives. Some also have measured radii and densities. Others reveal only part of the picture, as GJ 3378b does. This work may seem modest compared with the goal of finding life, but it cannot be skipped. Before studying an atmosphere, we need to know where to point the telescope. Before devoting many hours of valuable observing time to a planet, astronomers must determine its orbit, the most favorable moments to observe it, and whether the signal is likely to be strong enough. GJ 3378b is one of the targets placed on that map through years of patience. It is close enough to deserve attention, small enough for the possibility of a rocky surface to matter, and located within an energy range that does not immediately rule out liquid water. But the map we have today still resembles only a preliminary sketch. A point tells us that the planet is there. A curve reveals its orbit. A number gives its minimum mass. Everything else remains blank. No one knows whether GJ 3378b has an atmosphere. If it does, no one knows how thick it is or which gases it contains. The pressure at the surface is unknown, as is whether the true temperature is higher or lower than the calculated equilibrium value. The planet's radius remains another blank space. It may be only slightly larger than Earth and highly dense, or it may be more expanded because of water and gas. Without knowing its size, we cannot confidently place it among rocky planets, ocean worlds, or small mini-Neptunes. The surface is also completely hidden. It may consist of dark rock that absorbs most of the star's red light. It may be covered in ice that reflects energy back into space. A thick layer of clouds could conceal everything below, or the planet may no longer have enough atmosphere to form clouds at all. If water exists, it may lie on the surface, beneath ice, or deep within the mantle. If the water has been lost, no one knows when it disappeared. The planet may have been dry from the beginning, or it may have passed through an era of oceans before radiation removed most of its hydrogen. The history of the host star has not yet been fully reconstructed either. GJ 3378 may now be relatively quieter than it was in its youth, but the intensity of its flaring during the first hundreds of millions of years can only be estimated from models and comparisons with similar stars. A small difference in that history could significantly change the outcome for the atmosphere. The system may also contain other planets, smaller worlds, more distant worlds, or planets with longer orbital periods may not yet have produced signals clear enough to appear in the current data. A companion planet in an outer orbit could have influenced the dynamical history of GJ 3378b, sending additional comets into the inner system or altering its orbit in the past. Continued observations over many years may reveal new signals. Slower wobbles could point to a more distant planet. Small improvements in the current model could define the orbit of GJ 3378b more precisely. Precise measurements of the star's position may place limits on the orbital inclination and narrow the range of its true mass. Each advance will not necessarily produce a dramatic discovery. Sometimes, it may only mean a smaller uncertainty, an adjusted period, or one possible scenario being ruled out. Yet these small changes are what gradually make the picture more reliable. This is also how our understanding of GJ 3378b has already changed. The planet did not suddenly become lighter. Better data simply brought us closer to its true nature. Future telescopes will not transform the world into something different either. They may only draw back another part of the curtain concealing it. The first direct light detected from GJ 3378b may be too faint to provide a clear spectrum. New telescopes may only establish a limit on its brightness or temperature, or techniques that are still incomplete today may eventually combine many years of observations to separate the planetary signal from the host star. No one can know which instrument will provide the first answer. A giant ground-based telescope may detect thermal light. A future space mission may measure a reflected light spectrum. Another method may infer the presence of an atmosphere from its effects on temperature and brightness throughout the orbit. Whichever path succeeds, it will still require time. Light must be collected over many hours, many nights, or many years. The signal must be compared with models of the instrument and the activity of the star. Chemical traces must be tested carefully to avoid mistaking noise for a real molecule. Even if an atmosphere is confirmed, the questions will not end. A thick layer of gas would open many more unknowns involving pressure, clouds, the surface, and water. Every answer would reveal more subtle questions. That is not a failure of science. A world 25 light-years away cannot be fully understood after only a few observing seasons. The distance is close enough for light to reach us within part of a human lifetime, yet still so great that an entire planet is reduced to a faint signal beside a dim star. Throughout the history of astronomy, humans once knew the planets of the solar system only as points of light. Mars was once a red dot with no map. Venus was hidden beneath clouds so completely that no one knew the landscape below. Those worlds emerged only gradually as telescopes improved and radar, orbiters, and robotic explorers were sent closer. GJ 3378b lies so much farther away that humanity cannot imagine sending a spacecraft there in the foreseeable future. Everything we learn must be carried back by light, through photons that have crossed hundreds of trillions of kilometers before touching a telescope mirror. Each photon carries only a tiny part of the story. Some come directly from the star and reveal its temperature, composition, and motion. One day, photons reflected from the planet may reveal clouds or gases, but that faint light must be found among countless brighter photons from the host star. While humanity continues to improve its ability to observe, GJ 3378b keeps completing its short orbits. A little more than every 3 weeks, it returns to nearly the same position relative to the star. If clouds exist, they continue to move. If there is ice, it continues to absorb and reflect light. If the atmosphere is slowly escaping, atoms continue drifting into space without producing a signal large enough for us to see. There may be other worlds in the system moving more slowly, not yet completing enough orbits to reveal themselves in the data. Or GJ 3378b may be the only planet close to the star. The regions that remain unobserved are still far greater than those we understand. From Earth, Telescopes can only continue listening, measuring the same star with increasing precision, and waiting for technology to open new paths. There is no single doorway into the planet's secrets. Each method reveals only one layer: gravity, a transit shadow, reflected light, or thermal radiation. GJ 3378b has revealed the first layer. It pulls on its star, creates a regular rhythm in the spectrum, and confirms that a small world exists there. But it casts no shadow across the stellar disk, gives us no radius, and does not allow starlight to pass through its atmosphere along a favorable line of sight. The planet therefore remains like a room known only through the faint movement of a door. We know that something is inside and can estimate its weight from the way the hinges shift, but we have not seen its shape, its color, or the air within the room. Future telescopes may open that door a little wider. They may reveal a layer of gas still holding warmth around the planet, or confirm reflected light from a cloudless surface. They may also find nothing more than a signal too weak to interpret, forcing humanity to wait for another generation of instruments. Whatever the final result, GJ 3378b will remain valuable. If it has an atmosphere, it will help us understand how a rocky planet around a red dwarf can withstand intense radiation. If it does not, it will mark an important limit in the search for places capable of retaining water. Even silence can become data when instruments are sensitive enough to know what they are failing to detect. A distance of 25 light-years allows the planet to be called nearby, but that closeness belongs to the language of the galaxy. For humans, it is still far enough for an entire sky, a layer of clouds, or a rocky plain to become almost impossible to observe. We know that GJ 3378b exists. We know that a year there lasts about 21.45 days, that it orbits close to its host star, and that its mass is at least about 2.3 times that of Earth. We can sense its gravity through the tiny shift it creates in the star's light. But an enormous distance remains between a velocity curve and the sound of wind across a surface, between a number describing incoming energy and a real drop of liquid water lie an atmosphere, pressure, clouds, geology, and billions of years of unknown history. Between confirming a planet and understanding that world are countless layers of information that present-day telescopes still cannot reveal. Far away, GJ 3378b continues to orbit in the faint light of its red dwarf, carrying answers that humanity cannot yet read. Its sky may contain clouds, or there may no longer be a sky in any familiar sense. And while new generations of telescopes slowly take shape, the planet continues to conceal almost its entire surface, leaving behind only a faint gravitational rhythm that crosses the darkness and finally reaches Earth. In the northern sky, where the constellation Camelopardalis stretches across quiet regions of darkness that rarely draw attention, light from GJ 3378 is still traveling toward Earth. It does not arrive as a brilliant beam visible to the naked eye, but as a faint stream of photons, silently crossing the space between the stars before being gathered by the large mirrors of our telescopes. The light reaching Earth at this moment left that star about 25 years ago. When it began its journey, many things now familiar in our lives did not yet exist. During all that time, GJ 3378b continued moving around its small star, completing more than 400 orbits without producing a single sound in the vacuum surrounding it. Each orbit lasts only a little more than 21 days. A year there begins and ends before 1 month has passed on Earth. The planet follows the same path again and again, receiving light from its host star, pulling the star into a very slight wobble, and continuing a motion that had already been unfolding long before humanity knew it existed. From Earth, we have never seen the planet itself. We have seen only its influence. Within the star's light is a subtle rhythm of motion, a regular shift toward us and then away again, like the trace of something moving behind a curtain without ever stepping fully into view. From that rhythm, astronomers know that GJ 3378b has a minimum mass several times greater than Earth's. They know the planet orbits much closer to its star than Earth does to the Sun. Yet because the host star is small and faint, the world still receives an amount of energy close to what our planet receives. These measurements place GJ 3378b in a remarkable position. It is not a giant gas planet, and it does not orbit so far away that the possibility of water can be dismissed from the beginning. It may be a rocky world, perhaps massive enough to retain an atmosphere, and it lies in a region where temperatures would not theoretically prevent liquid water from existing. But beyond what has been measured lies a much wider space, filled with everything we still do not know. We do not know how large the planet is. We do not know whether its atmosphere has survived billions of years of exposure to a red dwarf. We do not know whether the star's faint light is falling on rock, ice, water, or a thick layer of clouds hiding the entire world below. GJ 3378b may be a rocky planet with an atmosphere dense enough to carry heat from the illuminated side toward the darkness. Within that atmosphere, water vapor may condense into clouds. Rain may fall over landscapes no one has ever seen, flowing into basins and remaining there beneath the dim red light of the star. If oceans exist, they may be unlike the oceans beneath Earth's blue sky. The light reaching their surfaces would contain more red and infrared wavelengths. The rhythm of day and night might be very different, or one side of the planet may always face the host star, while the other remains beneath prolonged darkness. Between those two regions may lie a broad twilight zone, where the star never climbs high in the sky and never fully sets. Winds may continually move from warmer areas toward colder ones, carrying clouds and water vapor around a planet whose year is shorter than one of our months. But it is also possible that none of these images exist. Radiation from the star during its youth may have heated the upper atmosphere, allowing lighter molecules to escape gradually into space. Water, if it was ever present, may have evaporated, been broken apart, and lost its hydrogen over hundreds of millions of years. The atmosphere may have grown thinner until there was no longer enough pressure to sustain oceans, clouds, or rain. In that case, GJ 3378b may now be nothing more than a silent sphere of rock. One side could receive nearly continuous light, while the other remains locked in deep, cold darkness. There would be no winds to redistribute heat, no clouds to soften the light, and no oceans to store warmth. Craters may have remained almost unchanged across the surface for billions of years. Low-lying regions that might once have held water, if they ever existed, may now contain only dry rock and minerals. The planet would still orbit within what we call the habitable zone, but a favorable location could not restore an atmosphere that had already disappeared. Both possibilities remain consistent with what we know today. A world with air and water has not been ruled out. Neither has a barren planet. The available data are not yet sufficient to place GJ 3378b on either side of that boundary. The fascination of GJ 3378b does not come from proof that life exists beyond Earth. There is no evidence of organisms living on its surface, no signal from a distant civilization, and no direct confirmation of water or an atmosphere. What makes this world important is that it is close enough for humanity to continue observing, small enough for the possibility of a rocky planet to be taken seriously, and positioned favorably enough that the question of water is more than mere imagination. In astronomy, a target like this is valuable because it can be tested. Not today, and perhaps not with the instruments currently in operation, but its light remains within reach of more powerful telescopes now being built and future space missions still being envisioned. One day, humanity may be able to separate the planet's faint light from the glare of its host star. Within that spectrum, there may be traces of carbon dioxide, water vapor, or other gases, or the instruments may find no substantial atmosphere at all, suggesting that the surface has been left directly exposed to space. Either result would be meaningful. If an atmosphere still exists, GJ 378b would show that a rocky planet orbiting a red dwarf can survive a harsh radiation environment. If the atmosphere has been lost, it would help define the limits of which worlds can retain water around the most common type of star in the Milky Way. And even if future telescopes provide only tighter limits, every measurement will still bring us closer to an answer. A measured radius, a more precise mass, or an atmospheric signal that is either detected or ruled out would make this world a little less uncertain. Science does not need to rush to turn a possibility into a belief. It can leave the question open, continue observing, and accept that sometimes the most accurate thing we can say is that we still do not know. Far away, GJ 3378b is not waiting to be discovered. It does not change because humans are pointing telescopes toward it. The planet continues along its orbit, the star continues to shine, and any processes occurring on the surface continue whether anyone is watching or not. The light leaving that star system today will reach Earth about 25 years from now. By then, telescopes may be different, analytical methods may be more precise, and humanity's understanding of planets around red dwarfs may have changed enormously. Yet during the time that light travels through space, GJ 3378b will complete more than 400 additional orbits around its star. If clouds exist, they will continue to drift. If there are oceans, their waves will continue to move. If only rock remains, the surface will continue absorbing light and releasing heat back into the darkness. No sound from that world can reach us. No horizon appears through our telescopes. There is only a small star wobbling ever so slightly, just enough to reveal that a planet is there. 25 light-years away, that world continues to orbit in silence, unaware that on a small planet circling another star, humans are patiently measuring the faintest movements in its light, trying to learn whether nature has ever created another place beyond Earth, capable of preserving a sky, water, and the conditions required for life. May the quiet orbit of GJ 3378b leave behind a moment of peace within the vastness of the universe, before the light of distant worlds continues drifting through the night.